Are you able to see the PPT?
Yes, sir.
Okay. Okay, we start today the same second chapter. Okay. So what we discussed in the last class, just I go for recap, first a couple of minutes, then we go for the today discussion. So in the last class we discussed the different types of stresses, and also we discussed the fluctuating stress, static stress we discussed. Finally, we discussed the fluctuating stresses, right? In the fluctuating stresses, there are three types of stresses we discussed. One is, completely reversed stress. Then second one is repeated stress. Then third one is fluctuating stress. Okay. So in that we discussed sigma mean, minimum stress, sigma max, maximum stress, and sigma m, mean stress means average stress, and sigma a, amplitude stress, amplitude stress amplitude, and r, as a stress ratio. So that's what we discussed in the last class. Today now we are going to discuss furthermore information about this topic. Now see here. Now see, as of now we know, right? What different types of stresses and components. What are the types of stresses the component going to be subjected when the component is operating condition, right? We discussed based on static deflection, based on static load. We discussed compressive stress, tensile stress, bending stress, shearing stress. These are under the static load we discussed, right? Bending moment, shear force diagram, SF diagram, and torsional movement. These are under static condition. And also we know that, static load is nothing but, when the force gradually applied on the component, that doesn't change with respect to time and direction of the component. The force component, the magnitude of the force and direction of the force doesn't change with respect to time. That's what we discussed in the static loading. But see here, the failure, any mechanical component or any machine component may fail due to that fail. Once the component fails occur, the component will not function properly. What are the possibility of failures? The major, we can classify in three ways. The failure with respect to elastic deflection, failure by general yielding, failure by fracture. Now we are going to concentrate first two: failure by elastic deflection, failure by general yielding. Failure by fracture, now we are not going to concentrate, but we are going to concentrate first two only. Okay. Now, but in generally, suppose if I'm considering the transmission shaft, supporting the gears as well as transmitting the power. But when the shaft reaches maximum force, right, without affecting the performance, is limited by the permissible elastic limit. Permissible elastic limit in that sense, we are considering here their lateral or torsional rigidity is considered for the design criteria. And for example, when the shaft is supporting the gears with the maximum power transmission, during that time, without affecting the performance of the shaft, is limited by the permissible elastic deformation. We are allowing the limited deflection. Elastic deflection. Means that within the elastic deflection, what we discussed in the stress strain curve, up to elastic behavior, we are allowing that shaft deflection. When we are considering up to elastic deflection, then the lateral and the torsional rigidities are important parameter for designing the shaft designing the shaft dimensions. Okay. Generally any design of any mechanical component All these cases based on the permissible and lateral deflection, permissible lateral, linear, and lateral deflection. Okay, I mean, we discussed a couple of problems also. I mean, what is this? I mean, within up to elastic limit, the stress may be the stress may be as 100 megapascal. We know that the stress is equal to force by area. Then we know the limitable. We know the limit stress limit 600 megapascal. Then we know the force, right? Applied force. Then we able to find out what is the area pi before d square. Then d able to find out. Simple concept. That's what we are considering here. The design of any mechanical component in the most of the cases based on the permissible lateral and torsional deflection. Okay, and now one more thing, the modulus of rigidity, modulus of elasticity, and modulus of rigidity also important parameters or properties for designing the component dimensions, because these two are material properties. Elastic modulus and shear modulus going to be a material properties. So these two also important parameters for designing the component. Okay. Now, if you know Young's modulus of the material, if you have a rod, the rod is a 10 mm diameter, right? Or the rod length is 50 centimeter, right? You know the material properties. For example, shear modulus, you know. Then you know the limits shear. I mean stress limit, shear stress limit. You know, then you know the. I mean, what is then Young's modulus? Shear. What is the shear modulus? Shear. I mean, shear stress divided by shear deformation, right? Shear stress divided by shear deformation. Then you have to apply the concept shear force. Shear stress is nothing but shear force divided by sheared area. I mean, force divided by sheared area divided by change in the original dimension, right? Sheared deformation, right? Now, if you know that, okay, I can briefly explain here. Okay. This is, oh my God. Okay, if you know the shear stress, I mean, you know the shear modulus, you know the shear stress constant. I mean, you know the shear stress. If you know the shear stress, you can apply this, right? I mean, shear force divided by sheared area. From that, we able to find out the rod diameter. Suppose if you don't know that, I mean, if you don't know this, or if you know this component, only if you don't know that material dimension, we can find it from the numerator component. If you know this shear deformation, so this way also we can define our dimensions of the component with respect to shear modulus and Young's modulus, elastic modulus. Okay, and I mean and where it is playing the yielding, we are saying that one is deflection, another one is yielding. Where is the playing yielding? Yielding. I mean, the yielding is nothing but you can consider local yielding and general yielding, generalized yielding. What is the generalized yielding and local yielding? For example, the localized yielding is nothing but the region of the stress concentration is restricted to very small portion of the component. For example, I draw the simple cantilever beam. Okay, when the load is subjected in this cantilever beam, maybe the cantilever beam subjected into yielding, then small region of interest, very small portion of the yielding going to happen here. For example, small region of the portion going to happen yielding here. But this small region of interest, this small portion of the region doesn't affect your component operating condition. But the same small region, yielding region, I mean, yielding going to happen in this region, maybe happen in this region. For example, this is now this region. Now this is a generalized yielding. because this region is more important for finding the for analyze the failure condition. So this is called localized yielding. This is called localized yielding, where the small region of interest when the the region of stress concentration is restricted to very small portion of the component in this region, but this region doesn't affect our component. But when the yielding is going to happen, particularly in this region, in the junction between the fixed position as well as that component beam, then this region is going to be generalized yielding. This region is very important for designing the component. This is called generalized yielding. The yield strength of the material is an important property when the component designed against failure due to generalized yielding. Generalized yielding. Okay. Now I come to this, component. See, we know the stress strain diagram. In the stress strain diagram, this is the, this is our brittle material. This is our ductile material, right? This is our brittle material. This is our ductile material. See here, in this brittle material, the brittle material without, this is strain. The brittle material without, with little deformation, it's going to be a failure. The failure may happen suddenly. Then in this situation, we cannot consider the ductile, elastic strength. Only we are considering the ultimate strength. We are not considering the brittle material for elastic limit stress. Only we are considering the ultimate strength. Because why we are not considering elastic limit? Because the brittle material, it's very little deformation, it will be failure occur. That with little deformation we are unable to predict. Hence we are considering, when we are designing the component based on brittle material, we are considering the ultimate strength. The material stress must be near to ultimate strength, above the ultimate strength. Then we can easily avoid the failure in the brittle material. So brittle material, always we are considering the ultimate strength, but not yield strength. Now come to ductile material. Ductile material this is yielding. We are considering yielding. Just because the ductile material even reached yielding strength after this is elastic limit. This point is elastic limit 1. This point is yielding strength. Even the material reached yield strength, the material doesn't failure, but still we can safely stop our operating function of the component. That's what we are considering this, yield strength in the ductile material. But because the sudden failure not happening in the ductile material, but here the brittle metal sudden failure is happening. Hence, for safer side, for safe limit, we are considering the ultimate strength. For brittle ductile material, we are considering the yield strength. Okay. Now, what is the factor of safety? Factor of safety. Factor of safety is, while designing the component, it is necessary to provide the sufficient reserve strength. Sufficient reserve strength in this case of accident. In this case of an accident, this is achieved by taking suitable factor of safety. This we have discussed already. The table, some table based on the load condition, based on the operating condition. We discussed earlier. Based on that, heavy load, medium load, high load, like that, we have to define the factor of safety. Suppose the component structure is complex, hence we have to go for maximum more factor of safety. The FOS value will be more than 2.5, more than 2.25, like that we discussed. Suppose the components are uniform geometry, for example, the factor of safety we can define less. Okay, because more complex geometry, unpredicted at which portion of the component going to be failure. We cannot predict. Hence, we are going for more factor of safety. The factor of safety value will be more. That we discussed in the table. Please go through that. Okay. So now, generally factor of safety FOS for avoid the failure. For avoid the failure, when we have to provide, we have for avoid the failure factor of safety. For avoid the failure, we have to provide the appropriate FOS factor of safety while designing the machine components. Okay, this is SYT is nothing but yield strength. Okay, yield strength. SUT is nothing but ultimate strength for brittle material. This is for ductile material. Okay, this is for brittle material. Now I come to these are the things already we discussed. Only few things we already discussed. Stress strain relationship is sigma, tensile stress is equal to, just a small conclusion here. P by A here, strain is equal to delta by L. This is the, deflection is equal to PL by AE. Anyway, now come to this stress strain relationship, shear strain, shear stress and shear strain. Shear stress and shear strain, where it is possible here. This is P by A here. The shear stress is going to happen in this region P by A, and then the shear modulus is equal to tau by gamma. That's what. Now here, what is this factor of safety when we are considering shear stress? Shear yielding. This is shear yielding divided by Fs. That's all. Okay, and this is shear yielding. We can compare with the shear yielding along with the yield strength during tension. Now, shear yielding, this is shear yielding compared with the along tension 0.5 SYT. This also we are going to prove in the later in the Mohr circle. When we are going to discuss the principal stresses, we are able to understand how it became. Tau 1 to tau is going to be 0.5. SYT. We are going to discuss in the later. Okay. Now I come to this. This is very simple. Stress. This is shear stress and shear strain relation. Now I come to the shear stress. Stresses due to bending moment. This is what is the governing equation of M by I is equal to sigma, B by Y is equal to E by R. Right? Okay, right? This is R. This R is nothing but our beam radius, while the beam subjected into bending. Beam radius. This is Y is nothing but beam dimension, depth of the beam divided by 2 Y. Now E is Young's modulus of the beam, sigma is the bending stress, M is nothing but bending moment, I is moment of inertia. This is which case this is suitable? Anyone tell me that which case this is suitable? This formula. This is when the cross section of the beam is uniform cross section. The cross section of the beam is non-uniform. We can't use this formula. Okay, directly we can't use this formula. We have to go for some other method. Okay, so now that's what we have been given. Briefly given here. See here, when the cross section is irregular, shown in this is figure. Now see here in this condition, and one more thing. But while defining the factor of safety, we would like to consider some of the parameters. What type of load is acting on the component, and design accuracy in the force analysis, and what is the material of the component, and what is the reliability of the component. These are the things we should consider, and the effect of failure and failure chances we have to consider. It's nothing but a S-N curve. And then testing method. What are the testing method? And service conditions. Either in the service condition, high temperature or low temperature, and how service condition and the duration of service condition. These are the things you should consider while defining the factor of safety. And more information, please go through our earlier discussed table. Okay, now I come to again here. Now this is the non-uniform cross section of the beam for finding the bending stress. One simple example concept we discussed in the earlier class, right? Similarly we discussed. Now this is only for this is uniform cross section. That the beam is uniform cross section, and the force acting on the beam on the plane before bending, after bending, the neutral plane doesn't deform. Okay, that's what I'm saying. The plane cross section remain plane after remain plane after bending, the plane of cross section. Okay, now when the beam is non-uniform, irregular cross section, we have to find out. These are the things we have to consider. I mean, IXG, moment of inertia with respect to centroidal axis. IXG is equal to nothing but in the integral of y square dA. This is first moment of inertia, right? Anyone tell me that first moment or second moment of inertia? Integral of y square dA. Integral of y square dA, first moment of inertia or second moment of inertia?
Second.
Yeah, second moment of inertia. Then now we would like to find out the, axis x1 with respect to centroidal axis, moment of inertia with respect to centroidal axis into ay square. Okay, ay squared, we already discussed simple concept in the earlier shear stress and bending stress when we discuss shear stress bending stress concept. Okay, for finding the bending stress in irregular cross section of the beam. Now I come to the stresses due to torsion moment. What is the governing equation here? T by J. T or T I can consider here MT. T by J is equal to G theta by L is equal to tau by R. See here, there capital R. Very don't confuse. This capital R is beam radius, not circular cross section of the beam. While the load is acting on the beam going to be curved behavior in beam bending. This is suppose this is the beam. Now when the load is acting, this radius is, I'm saying that R. Okay, but in this case, in the torsional case, this is the radius is nothing but the component radius, this radius. Okay, now see, apply here tau is equal to mt by, from this governing equation we can obtain these relations. Tau is equal to mt into r divided by j. Theta is equal to ml t or ml or tl by gj, like that. Then theta, when you put j value is equal to id power 32 because circular rod, then substitute here, you are going to get theta in terms of radians like this. This is a general term. Power is equal to 2 pi nt divided by 60. 2 pi nt, here I am considering torsional moment is now I am considering the notation mt, 2 pi n mt divided by 60%. Okay, so these are the things to be it will be required when we are going to discuss the problem. Now we move to the eccentric loading. Now eccentric loading, what eccentric axial loading? In this eccentric axial loading, see here, there are certain mechanical components are subjected into the external force, tensile or compressive, which doesn't pass through the centroidal of the cross section. The load acting on the component, it's not necessary to always passing through the centroidal of the axis. It may be offsetted from the centroidal axis. Hence, now we are using this concept here, principle of, based on the principle of static, the force can be replaced by, now this is the offset force. This is the offset force from the centroidal axis. Now I am using this concept, principle of static. The force can be replaced. The force can be replaced by the force acting on the centroidal axis and passing through the offset position, then creating the bending moment. You might have been discussed in, I tell you small example. Now this is simple cantilever beam. When you discuss, this is load is acting. What do you consider here? When the load is offsetted, the load is offsetted. Now what do you consider? Now this is the beam is now subjected to bending moment as well as now this beam is subjected to this load is passing through like this P, right? Now the distance may be 0.2 meter. Then what is this? The bending moment now acting in this moment is now nothing but 0.2 times of P bending moment, right? That is at this point C. I may be considered point A, B, C. Now this is called a principle of static. Okay. Now this is the offsetted load. The offsetted load now splitted into axial load as well as the couple. Couple is nothing but moment. Similarly, I would like to apply the same concept here. The P is now acting in the axis of the component, and the P is always generating the moment Px into E. P into E, not X. Sorry, this is not X. P into E. The offset distance is E, then P into E, the moment acting here. Now, when we are considering, now the load is acting in upward direction, right? When we are considering this, these are the uniform, this is the average stress in the upward direction, because this is the tensile load. Now, based on movement, now the beam is subjected to bending moment. The beam is not beam, the component is subjected to bending moment, right? Bending moment in this direction, right? Anti-clockwise direction, right? Now, when the bending moment acting in this component, this layer, this is considered as a outer layer. This layer is considered as a inner layer. Then this layer going to be subjected into compressive. Obviously, this layer going to be subjected into compressive with respect to bending moment direction. Okay, this is layer going to be subjected into compressive. This layer going to be subjected into tensile. This is a compressive. This is a tensile. Then I can draw the diagram like this. Bending stress diagram. Bending stress distribution along this component. Right now, this component only we are splitting like this, one curve like this, right? First, I considered the axial force, then I considered the bending moment. Then see, add these two components, add these two stress distribution. Then what will happen? This is upward direction. Obviously, the left side, this portion going to be in opposite sign of the sign. Hence, it will be less. When we are considering resultant stress, then finally this side going to be less, because this side opposite upward direction. This side force is compressive. This side force is tensile. Obviously, when we are using principle of superposition, then it will be less here. This region less. But when we are considering this side, that is a tensile force and tensile stress. Then here also the stress component in same direction. Then based on superposition, it will be more. It will be summation. It will be a summation of these two. Summation of this right side component. Summation of this right side component. It's going to be like this. Okay. So now finally we can say that plus or minus P by A plus or minus P into Y. E is our eccentric distance. Offset distance, Y is nothing but our d by 2 depth of the component divided by 2. Now when you are considering P by A minus PEY by I is nothing but this region, this stress. This is nothing but P by A minus PEY by I. Now this is the plus region, P by A plus PEY by I. That's all. Okay, now I come to state of stress. Now, state of stress, we discussed this component. I'm not going to spend more time in this. See, why do we require? That's what we are going to discuss here. On a given area, we may have some normal stress and some tangential stress. These stresses together define the state of stress. See here, whatever we discuss in the strength of material, the rod is uniform cross section, we apply the tensile load. But when we are going to deal with the machine components, the components are not uniform cross section. The components are complex section, but each component is going to have a normal stress, or some components going to have shear stress, or some components going to have both normal and shear stress. Then in this situation, we cannot consider the average stress. For example, for your clear understanding, this is subjected to tensile load. This is considered average stress. Okay, but when the component are irregular cross section, the component in irregular cross section, 1 minute, I drawn it somewhere. Yeah, the component are irregular cross section. For example, small rod like this shape. Now, this is change in boundary, change in the geometry. Then, I mean, each point, the stress component going to be varying with respect to direction of questions. Hence, we would like to find out the state of stress at each point of the component. Then we have to play with the three-dimensional stress component. Suppose if I am taking one element here, this element I am assuming that when the load is acting, here may be vertical load and horizontal load and this here like that. When the component subjected to multiple load, then I mean this component, then the component is now in complex structure, not uniform geometry. Hence, each element at each point we would like to analyze the stress component. Hence, that's what we are using this stress tensor. Okay. Now, in this component, we may consider the complex load is acting, right? Complex load is acting. Then each component, what is the stresses? Because I mean, corresponding, maybe this region may be a different direction cosines. This region may be a different direction cosines. This region may be a different direction cosines. Then based on that, we have to define the state of stress at each point of the component when we are dealing with complex geometry. Okay. Now I mean, see here, now the shear stress is applied on the surface of the reaction. We may get a 3 stresses, what we discussed at the very beginning of this topic. Now this is subjected to 9 stress component. The 9 stress component reduced to 6 stress component, because 3 normal stress component, these are normal stress component. Okay, these are normal stress component, sigma x, sigma y, sigma z. These are the, I mean, shear stress component. This is the 6 shear stress component. With respect to complementary shear or cross shear, we are considering 6 shear stress component. Now 3 shear stresses, tau xy is equal to tau yx. Tau x is equal to tau zx, like that. Then tau y is equal to tau zy, like that we are considering. Finally, we are coming to 6 stress component. Okay, while playing with the triaxial loading system. When the component is subjected into triaxial loading system. Now I come to the this matrix. This is what is this? This stress tensor. This stress tensor also symmetric stress tensor. When we are considering this cross shears or complementary shear, tau xy is equal to tau y is x, tau yx, tau x is equal to tau zx, like that. Then this is symmetric tensor. I mean symmetric. Now biaxial loading. In biaxial loading, we are considering only 2 stress component. This also we discussed, sigma x. I mean when the plate subjected to sigma y vertical load and horizontal load. I mean this plane subjected to stress sigma x, this y plane subjected into sigma y. Then these are the component is here. Then based on that we can define this stress tensor sigma x, sigma y, and tau xy, tau yx, like that. Now what is the state of pure shear? Can you tell me? Someone tell me that. Suppose it's pure shear means what is the triaxial loading tensor? Can you tell me that? Pure shear, how can I write a triaxial loading tensor? Suppose this is a pure shear. Can you say that?
All the diagonal elements will be 0, sir.
Yeah, thank you. Exactly. Okay, now this is the some more things. Okay, see here, and yeah, this is just recap. I mean, this is the uniaxial load, right? I mean, leave it about rubber. Now come to chalk. I mean, for example, brittle failure. I told you that with little deformation, the material going to be failure, right? If you take any chalk, small chalk piece, I mean, highly brittle material, right? When you apply the load, the deformation will not be observed. Okay, within little deformation, the chalk going to be failure. For example, I am putting here, this is because of the chalk going to be failure. That is hence we are considering the ultimate tensile strength for the brittle materials. While using the brittle material for designing the mechanical component, we are considering the UT, ultimate tensile strength. I mean, for example, another example I am giving here for twisting. When you apply the twisting moment in the brittle material, for example, chalk, it's easily deformed, easily broken without absorbing the deformation. Okay. And another example, see here, the transmission of shaft. Transmission of shaft here, this is subjected into bending. This is subjected into bending, subjected into axial load, subjected into twisting moment. Then how can I write? Here, this is a direct stress, right? This is the load acting W. Load acting W. And T is the torsional moment, twisting moment. Then how can I write? I mean, in this case, the component subjected only torsion, then shear, only shear stresses. Now in this case, with respect to torsion moment, shear, right? And sigma B, nothing but bending stress. Sigma D is nothing but P by A, direct stress, right? Direct stress. But bending stress, how can I define? You already might have studied the 32 WL by pi d cube. This bending stress, this is the shear stress. The 16T divided by d cube. From this earlier equation, whatever we discussed, that equation, governing equation T by J is equal to G theta by L is equal to tau by R for torsional stresses. Torsion moment, governing equation. Bending moment governing equation, M by A is equal to sigma B by Y is equal to E by R. From that relation, we derived this formula from that formula. Okay. Now this is subjected to shear, bending, and direct stress. Okay. Now I come to the principal stress. Principal stress. Principal stress. What is the principal stress? Anyone? Please tell me that. Principal stress. You already studied, right?
So maximum and minimum normal stresses.
Yeah. See, first of all, why do we need why we are studying the principal stresses? For designing the component, we should understand. Then we can easily use this concept while discussing the problem. See here, there are many components which are subjected to several types of loads simultaneously. Maybe tensile or compressive or shear or bending or torsion, whatever. Several components, depends on the component operating condition, operating position, okay, and shape of the component. It will be subjected to several stresses corresponding, several loads corresponding stresses. For example, transmission of the shaft. The power transmission of the shaft is subjected to bending as well as torsion, right? That is, hence we would like to, we have to determine the state of stress under each condition. When the component subjected to variable stresses means different stresses. Each of these stress we have to determine while designing the component. Okay. Now I come to this. Just we briefly see this, then we go for the theory of failures. Now I am considering this small element. A small element subjected to biaxial stress. One is sigma y, sigma x, and obviously tau yx, tau xy going to be there when these stress components are acting for tau xy, tau yx based on the stress tensor. When two stresses are acting, sigma x and sigma y is normal stresses, right? then tau yx and tau xy is a complement. Tau is a shear stress, but tau xy and tau yx are complementary shear stresses, right? Now I'm considering in this component. I mean, see, this is the I consider this is our oblique plane. This is our oblique plane. Why we are considering? See, for example, now I am taking small, for our understanding, I am taking small rod bar. See, I am applying the load here, P. Here I am applying the load, P. Here also I am applying the load P1. Here also I am applying the load P1. Okay, now I mean the rod is the bar. Sorry, the bar is now uniform cross section only, but the bar is subjected to tensile load. I mean biaxial load, right? The bar is subjected to biaxial load. But at which case the bar is going to be failure happen. But which case the shear stress is acting in the bar? We should analyze it, right? Why do we need that? Because the bar, we can say multiple planes. The bar is it can be divided into multiple planes. See, for example, I can divide this bar. I can divide this cross section of the bar in multiple planes. Multiple planes. One plane may be here, right? Another plane may be here, right? Then multiple planes I can define this bar, right? You can slice it in multiple angles, this bar, but at which plane the maximum shear stress is acting? Because the bar is looks like now only normal stress is acting because these two planes are perpendicular, but the bar, it can be sliced into infinite planes at infinite angle. Are you understanding? Now, infinite angle. Hence, simply I draw it here. Now the bar is subjected to this plane. This plane, the angle is some theta. For example, I am slicing into one plane. You can slice into multiple planes, infinite number of planes. Alright? The infinite number of planes, which plane is going to have which plane is going to have the shear stress is maximum shear stress? Because, I mean, suppose the crack is propagating inside the bar, right? Suppose the crack is propagating inside the bar and 45-degree angle plane, then the maximum stress is acting in that 45-degree angle plane, because that's what we are going to study here. Now, that's what I considered here the bar. I mean, the rectangle element I consider like this. Okay. Now, I mean, these are the stress components: sigma x, sigma y, tau xy. I know the theta now. Now you apply the equilibrium force condition, equilibrium force concept. Now, I mean, the normal stresses are sigma x, sigma y. Shear stresses are tau xy, tau yx. Right. Now tau xy and tau yx. Now apply the equilibrium force condition to define this tau and sigma, which is acting on the oblique plane. In the oblique plane, I consider the oblique plane is sitting theta angle from the axis of the bar. Axis of the bar. This bar. For example, this bar. This bar. Axis of the bar, the oblique angle is sitting on the theta angle. Okay. In this plane, what is the stress component? What are the stress component will be there presented? Will be tau and sigma. In this tau and sigma, based on this component, we are going to find out using the concept. I mean, using the concept equilibrium force condition concept. Okay, then we came to know that this sigma x equals sigma x plus sigma y by 2 plus sigma y by sigma x minus sigma y by 2 plus into cos 2 theta plus sin tau xy sin 2 theta. This is for tau component acting on the oblique plane. Now similarly, sigma acting on the oblique plane. Now tau acting in the oblique plane minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. These two components acting in the oblique plane when I'm splitting oblique plane. Okay. Now, if you consider, if you changing the theta, changing the angle, then sigma and theta will keep on varying. When you are changing the angle. Changing the angle means we are trying to change the plane angle, the oblique plane angle. We are trying to change with respect to axis of the bar. Okay. Then it will be changing, but at a particular value, the tau going to be 0. At a particular value, the tau is going to be 0. Then during that time, only the sigma only exists. This sigma only exists. For example, this plane. Okay, in this plane only, P only exists. Sigma only exists. That is called principal stresses. That particular plane is called principal plane. Corresponding is principal stresses. Okay. Now I am considering the biaxial load number. That's what I explained here. Now I would like to consider how to find out my sigma 1, sigma 2. Now take this equation first. Now I would like to differentiate with respect to theta, because as I told you that changing the theta, then I would like to differentiate with respect to theta this equation, then equating 0 to find out the maximum principal stress. Okay, now differentiate with respect to theta, then this time going to be 0, then this is going to be, briefly I explained that. I'm not going to deep information. This is going to be, now this is going to be, what is this? Tan 2 theta. When you differentiate with respect to theta and equal to 0, this is going to be tan 2 theta. Is tan 2 theta is equal to tau 2 tau xy divided by sigma x minus sigma y. Obviously it will come like this. The 2 going to be come here. Sigma x minus sigma x here. Sigma x minus sigma y by 2. Now this is a tan 2 theta. Now if you, based on this tan 2 theta, you can draw the rectangle triangle here. This is the adjacent side. This is the adjacent side, this is the opposite side. The tau xy going to come here, tau xy. This is our adjacent side, this is opposite side, this is adjacent side. Sigma x minus sigma y by 2. Now this is our square root of this component, right? Now see here, this is theta. Now we are able to define what is cos theta. Cos theta is equal to nothing but sigma x minus sigma y divided by 2 square root of this component, right? Then substitute again this equation. Sin 2 theta. Sin 2 theta is equal to tau xy divided by square root of this component. Then we are able to find out sigma 1. Similarly, tau value differentiate with respect to theta equal to 0. Then equating to 0. Then finally you are going to find out, this relation, that is tan 2 theta. Here also tan 2 theta is equal to sigma x minus sigma y divided by 2 tau xy. Okay, now in this case, again you formulate this rectangle triangle here. This is adjacent side. Which is one is adjacent side? This is going to be sigma x minus sigma y by 2. This is tau xy. Now this is theta. Now from this we can find it out as sin 2 theta and cos 2 theta. Then substitute from this, this sin 2 theta from this diagram. You can define the sin 2 theta. From this diagram, sin 2 theta, you can define cos 2 theta. Define again, submit in this tau equation. You are going to find out the tau max. Tau max finally plus or minus square root of sigma x minus sigma y by whole square divided by 2 whole square plus tau xy. Okay. Now this is the now maximum principal stress, maximum principal shear stress, maximum principal stress and maximum principal shear stresses. Okay, now come to the we just briefly discuss about the Mohr circle. Now, I mean, what is the important role of Mohr circle here? I mean, we know the value here, the stress, I mean, principal stresses we know, principal shear stress we know, but we would like to understand the graphical representation of these principal stress values. We would like to understand these principal stresses values in the term of graphical representation. Hence, we are using Mohr circle concept. The guy who found this concept, graphical representation, that guy name is Mohr. Then we are using his concept for graphical representation of the principal stresses. Okay. Now see sigma x and sigma y. Sigma x is our, I mean, this is our sigma x. Sorry. This is our sigma x. This is our sigma y here. These are the normal stress. I mean, O to C, normal stress with respect to x-axis. O to A, this is origin. O to A, I mean, normal stress, I mean, with respect to y-axis. Okay. 1 minute. I may be doing mistake. Am I right? Yeah, sorry. This is x. This is, sorry. That's what. This is sigma y, this is sigma x, sorry. Okay, now OA is sigma x, OC is sigma y. Then, I mean, at the point I mean C, at the point C, we are pointing the y-axis. Y-axis in the Mohr circle, y-axis representing the shear stress, x-axis representing the normal stress, right? Then tau xy we are pointing out in the y-axis corresponding to sigma y. Tau xy again we are representing corresponding to sigma x, right? Then where this intersecting, that point we are, based on that point we are plotting the Mohr circle. In this Mohr circle, this is our maximum shear stress, tau max. This is plus. Now whatever we mentioned here, plus or minus, this is plus tau max maximum. This is tau mean minus tau mean. This is minus sign. Okay. Now this is, now where is our sigma 1? When you draw the circle, this is OF. This is OF is our OF. This is OF. Corresponding dimension going to be sigma 1. Now sigma 2 is corresponding OG. This is OG, sigma 2. OG, sigma 2. Okay. Now where is our sigma n? Sigma and tau. This is our sigma, no? This is our sigma. Where is this sigma and tau? I would like to, where is this sigma and tau? This sigma and this tau, where I can write it? Where? This should be here. That should be here. Because this is a plane. This is the oblique plane. That's what we, you see here, parallel you see here. This is oblique plane. In this plane, this is a perpendicular to acting. At where this is acting perpendicularly, that is called sigma and tau component. I mean, in this graph, xy graph, here xy graph is nothing but sigma tau graph. The coordinate tau and sigma and tau, it can be identified this place, because this is the oblique plane. In this oblique plane, at the origin, my stress component and the shear component and the stress normal stress component, shear component acting in this, in the oblique plane, I can represent this point coordinate sigma and tau. Then draw the line here. This is our tau, sigma and tau. Okay. Now this is the very important when we are going to discuss the problem. So now I move to, now see here, this is a graphical representation. We are dealing with the two-dimensional graphical representation, but when we are going to study PG, people are going to discuss in the three-dimensional way. Now three-dimensional way, I mean, one more condition. I mean, here sigma 1 is nothing but sigma 1 sigma 1 greater than sigma 2 greater than sigma 3. This is a standard condition we are following. Then sigma 1, sigma 2, sigma 3 is nothing but three principal stresses along with the three principal direction corresponding to x, y, z. This is the principal stress with respect to corresponding direction x, corresponding plane x, this is a corresponding plane y, this corresponding plane z. When these stresses are equal, what will happen? Sigma 1 is equal to sigma 2 is equal to sigma 3. What is the condition? We can say that. Anyone? Sigma 1, sigma 2 or sigma 3 are equal, then what do you say that? Yeah, please someone reflect. And also tau max, sigma 1 minus sigma 2 divided by 2. This also I would like to represent. Sigma tau max also you can say that sigma 1 minus sigma 2 divided by 2. But what is this point? I mean this point sigma x plus this center point. This center point, I mean this is very important. You may get it in the gate question. Sigma, this is the point, sigma x plus sigma y by 2. Okay. Now I come to this. I mean, some more point we would like to discuss here. I mean, here the every point on the circumference, every point on the circumference of the Mohr circle, every point on the circumference of the Mohr circle represent the state of stress at a particular system. Every point, either maybe here the coordinate you may consider here. You may consider here, or you may consider here, you may consider here, you may consider here, you may consider within this region. Within this region, we may say that also, I mean, safe region. Beyond this curve, I mean, somewhere the component, I mean, this is a sigma 1, sigma 2, sigma 1, sigma 2, your value, that the coordinate value is sigma and tau is exceeding from the, away from the curve, that is not safe. That is not safe for the design the component. So whatever we are finding the stress component sigma and tau, so that should be within this region. Because why I am saying that? Because this plane, I told you that this particular plane we are considering in the bar, in the rectangular bar, which one I have drawn early. But in this rectangular plane, we can split in infinite number of planes. When you are slicing infinite number of planes, each plane is going to have different coordinates. Sigma tau 1, I mean tau 1, tau 2, tau 3, sigma 1, sigma 2, sigma, I mean sorry, not sigma 2, sigma 3. I mean this coordinate, it may be sigma first frame, tau first frame. Suppose if I am taking another plane that the coordinate may be sitting here. I mean tau second frame, sigma second frame, like that. So infinite number of planes are passing through the bar, then that each plane should be the stress component sigma and tau should be within this Mohr circle region. Then only we can say that safe limit. Otherwise it's not safe limit. If exceeding from the Mohr circle, it will not be a safe limit. Now furthermore we can discuss here. I'd like to take this one. Okay, already 4:09. Okay, please give me 10 minutes. We finish it, and tomorrow we'll say remaining thing we'll discuss tomorrow. Sorry. Yeah. Now see here. Suppose, I mean, see here. Now while only the load P is acting. Now anyway, sigma 1 by sigma 2. Now please tell me this. Tau max. Only tau max. Tau max is equal tau max. Then what is the stress component in this case? What is the normal stress component in this case? I mean tau max. So take this Mohr circle diagram. tau max may be sitting here, right? Now what is the tau max? Maybe I'm considering P. What is the normal stress component here? In this case, what is the normal stress component? Sigma 1, sigma 2. In this case, I mean tau max I have given you P. What is the normal stresses? I mean, principal stresses, sigma 1, sigma 2. Yeah, please. I'm expecting answer from your side. Hello? Hey, boss, I told you, this class I'm going to take at least 1.5 hours. But anyway, I have a class in the next hour. I try to complete within 5 to 10 minutes. Yeah, please reflect. What is the normal stress component? I mean, tau max is equal to P. I have given you P. What is normal stress component here? Normal stress means, here, principal stresses, sigma 1, sigma 2. What is sigma 1, sigma 2 here? Anyone? Hello? Kalyan, are you there in the meeting?
Yes, sir.
Yeah, you can. Anyone, please tell me the answer, boss. Did you study this or not? Now I have given you tau max is equal to P. What is the normal stress or principal stress? In this case, we can say sigma x is equal to sigma 1, sigma y is equal to sigma 2, right? Okay. Anyway, see here, if you draw the circle, I mean, in this case, this is our maximum radius, right? This is the radius of the circle mentioned tau max, right? Now what is this? This is obviously, I mean, this also same, no? P. Sigma 1 is equal to P, sigma 2 is equal to minus P. Okay. Now, when you are considering here, this, when you are considering sigma, sigma 1 is now P, sigma 2 also P. Similarly, here sigma x is equal to P, sigma y is equal to minus P. Now, next case, this is, I can consider the diagram like this when the object is subjected to into only shear component. In this case, the plate element. Okay. Now, tell me in this diagram, suppose sigma, this case, what is this? This case. This case, sigma y equal to 0. In this case, this is our sigma x, right? Now this is our tau max. Now what is this? This is in this case, what is tau max? Very important. This in this case, what is this? This is uniaxial load or triaxial load. I might have been erased this. This is uniaxial load or triaxial load or biaxial load in this case.
Uniaxial.
Yeah, uniaxial load. In this case, this is uniaxial load. Then sigma by 2. Because sigma 1 minus sigma 2 divided by 2 is equal to tau max. Then here tau 1 is 0, tau 2 is equal to 0. Hence, tau max is equal to P sigma by 2, sigma 1 or sigma x by 2. Okay. Now, uniaxial. Now, and another thing, when this element is subjected to P P. All the directions are P. Then what is this here? I mean Mohr circle. All are in P. Mohr circle. Sigma 2 is equal to, in this case, what is the Mohr circle? This is, what is, are you heard about the hydrostatic stress? In hydrostatic stress, suppose a small element, small bar is immersed in the water. The forces are, all the directions of forces are same or different? Same, no?
Same, sir.
Yeah, that is called hydrostatic stress. Okay. So when sigma 1 is equal to sigma 2 is equal to sigma 3, then this is a point. This is the point, sigma in the Mohr circle. It's Mohr circle in the principal axis only, not in the, the Mohr circle will be in the point. This is sigma. Okay. Now there are different cases, and one more case I'd like to ask. What is, compression? This is unit. Can you tell me this? Sorry. This is representing, what is representing this Mohr circle?
Compressive loads.
Yes, uniaxial
Compressive load.
compressive, yeah. This is tau max. This is our sigma 2 is there. Sigma 1 is going to be 0. I mean, similarly, you can draw in many ways, and a tau max occur, which plane tau max occur? Maximum load, maximum stress. For a bar, I am considering a bar. This is the bar now subjected into P. This is subjected into P. This is the plane. At which angle? At which angle that maximum shear occur? Which plane it will be occur maximum shear? 45-degree angle. Okay. This also you should know, and that's all. I mean, uniaxial strain. This is uniaxial compression, uniaxial tension, and plane stress case. Okay, now one more condition I will give you. How many Mohr circle you able to draw? Suppose sigma 3 I am considering 0. Okay. Now how many Mohr circle you able to draw? When you are considering plane stress case, sigma 3 I am considering 0, hence plane stress case. Okay. Now how many Mohr circle you able to draw? This is a tau. This is sigma. Then how many Mohr circle you able to draw? I mean, sigma 1 not equal to sigma 2. Okay. How many Mohr circle you able to draw? Here I am considering sigma 3 is equal to 0. Okay, this case. This case is I am considering sigma 2. This case I am going to consider sigma 1. This is sigma 2. Now, I mean, what is the Mohr circle radius? Mohr circle radius we know very well now, right? Sigma, I mean, tau max is equal to sigma 1 minus sigma 2 by 2. I mean, not only this, I can consider the tau 1 2, because I am considering the first plane and second plane. Sigma tau 1 2. Now, tau 1 3 is equal to sigma 1 minus sigma 3 by 2. Now, tau 2 3 is equal to sigma 2 minus sigma 3 by 2. Now, in this case here, I mean, sigma 1 is here, sigma 2 is here. Then I can, sigma 1 minus sigma 2 divided by 2 going to come here. Maybe coming here. Okay. Now, based on this, I can draw one circle. Based on this, I can draw the one circle. Sorry, I draw wrongly. Please give me a time, I correct it. The last discussion today. I can draw this. Sigma 1 is here, not this line, okay? Now, with respect to this circle, I have drawn one more circle. This is based on tau. This is tau radius of the Mohr circle with respect to sigma 1, sigma 2. Then I am going to draw with respect to sigma 1 and sigma 3. Sigma 3 0. Then sigma 1 by 2. Sigma 1 by 2 going to come here. Sigma 1 by 2 going to come here. Then based on that, I can draw the bigger circle. Here sigma 3, here sigma 1. Now based on sigma 3 and sigma 2, I can draw the Mohr circle. Tau 2, 3 is nothing but sigma 2 divided by 2. Sigma 3 is 0, na? Sigma 3 is 0, sigma 2 by 2. It will be a center point here. Then I can draw the another circle. Then how many circles we able to draw? 3 circles we able to draw while using plane stress case. Plane stress case we able to draw 3 circles. Okay. Three circles you able to draw that. Okay, please, if you have any doubt, please go ahead. I stop it here. The next class, I tell you what are the things are there still. Okay, this is already discussed. This is theory of failures. This 3, that's all. Then we are going to discuss the problem. Sure, next class we are going to discuss the problem. I mean, this first half an hour we discuss this theory of failures. There are 5 theory of failures. We discuss and we start the problem. Anyway, we are going right speed only. No, don't worry. So now please go ahead. If you have any doubt, please tell me. I come to chart box, someone. Yeah, thank you, Sumant. Plus P minus P. Okay. Any doubt? Amarnath, are you there in the meeting?
Yes, sir.
Yes. Any doubt?
No, sir.
Are you asked a number of doubts in the first year? Now you are not asking doubts.
Sir, online, sir.
Eh?
Sir, we don't have that physical connection, sir. That's why.
Okay. You asked many questions, no, during first year.
Yes, sir.
Yeah, really, I appreciated that time. Okay, guys, if you have any doubt, please, I'm ready to clarify your doubt. So next class, we are so sure we are going to start the problems. Next, at least 2 classes, we are going to discuss the problems only. We are going to discuss the different types of problems. All the information, whatever we discussed, we are going to use that in the problems for designing the components. Okay, guys. I mean, Kalyan, are you there in the meeting?
Yes, sir.
Okay. Shall we close the meeting?
Yes, sir.
Okay, guys. Thank you very much. And okay, we'll see in the next class Monday morning. And I'm requesting that Monday morning I can take 8:30. You are requested 8:30 class, right?
Yes, sir. You.
Yeah, please. Thursday I can't do. Thursday I have a class. Next class 10 o'clock.
Okay. Sir.
So only
Monday.
Monday I will take. Monday only I can take 8:30.
Yes, sir.